Hello teacher, I am Arife. We will explain to you about the effectiveness and cost of a verification and validation plan and the SQA, so software quality assurance model. I will talk about the data required for the SQA model. One of my good friends, Esranur, will explain the SQA model, and Duygu will explain application of the SQA model for comparing V and V plans. Before I talk about the part I want to make an introduction about the software quality assurance model and verification and validation plan. The software quality assurance model is an effective tool to provide project planners with estimates of effectiveness of a verification and validation plan. Such a tools enable to compare alternative programs when implementing a particular validation and verification plan by providing a percentage of error during the screening phase and affected cost of realizing the plan. This estimation method can also be useful for software quality assurance function when evaluation project plans. In addition, this model deals with two quantitative aspects of a V and V plan consisting of various defect detection activities. The plan itself will be integrated into a project's development process. First one, the V and V plans total effectiveness in removing project defects. Second one also be the V and V plans total cost of removal project defects. Now I will explain what is required to implement this SQA model. The SQA model has three types of data for the implementation of the model. First one, defect origin distribution. Second one, defect removal effectiveness. Third one, cost of defect removal. Now I will explain first one, so defect origin distribution. Defect origins, so the pace in which defects were introduced. Whatever defects origin are distributed throughout the development process from the project initiation to its completion. Surveys conducted by major software developers such as IBM and TRW and summarized by Jones based on 208 rule patterns of defect origin distribution. We may assume that this pattern has not changed substantially in recent years. Now, let's examine a characteristic distribution of software defect origin. These are software development pace, requirement specification. I will tell average percentage of defects originated in pace. Requirement specification, 30% design. The requirement specification 20%, design 35%, coding 35%, in this 35%, unit testing 25%, and integration 10%. Last one, documentation also 10%. Second one, defects removal effectiveness. A certain percentage of defects present in any quality assurance activity are filtered, which means that the percentage of defects removal is slightly lower than percentage of detected defects. This is because some fixes are ineffective or inefficient. In addition, these corrections are approximately 10% according to Jones 2008. The remaining undetected and uncorrected defects are passed on the successive development stage. The next quality assurance action implemented is determined for the defect combination. In this way, less over after previous quality assurance activities and new defects created in the current development phase. In this table, we see average filtering effective by quality assurance activities, again based on Jones 2008 and Jones 2011 and Pressman and Maxim. Uh, these are also 2015. Software development pace again, these are average percentage of defects originating in pace. I will read them. Requirement specification review 70%, design inspection 55%, design review 50%, design review after design inspection 30%, code inspection 65%, unit tests 60%, unit test after code inspection 35%, integration test 50%, documentation review and system text acceptance tests also 50%, both of them. Last one is cost of defects removal. According to data collected about development project the cost of removing the detected defects varies according to the development stage, and as the development process progresses, your cost increases significantly. And this is our last table. In this table, we see again average filtering effectiveness by quality assurance activities. Requirement specification review, and I will explain these words: requirement specification, design, unit test, integration testing, documents. Requirement specification review requirements is 1. Design inspection requirements 3.3 design 1. Design review requirements 3.3 design 1. Code inspection requirements 7. Design 2.1. Unit testing 1. Unit testing requirements 7. Design 2.1. Unit testing 1. Integration testing 18 for requirements 5.5 for design 2.6 for unit testing 1 for integration testing. Documentation review again 18 for requirements, 5.5 for design, 2.6 for unit testing, 1 integration testing, 1 documentation. System testing or accessibility testing, 52 for requirements, 16 for design, 7.4 unit testing, 2.9 for integration testing, 2.9 for documentation. Last one, operation by customer. Requirements is 103, design is 31, unit testing 15, integration testing 5.7, and then last one, documentation again 5.7. I will example for this information. For example, rectifying a design flaw detected during the design phase might require an investment of 1 business day, but it may take up to 16 working days to correct the same defects during acceptance tests. And I want to explain attention for this table and this table. It should be noted that according to these data, software development lifecycle is based on findings from project developed according to sequential process and may not represent project developed according to an incremental delivery model or an agile methodology. Now, my groupmate Esra will explain the software quality assurance model. Thank you for listening to me. Take care. Thanks.
Hello everyone, my name is Esranur ERSAN, and my friend Arife talked about the data required for the software quality assurance model, and I would like to explain more about the actual software quality assurance model. So I'd like to start with this model assumptions first. So the model based on assumptions such as development process, which is linear and sequential, following the waterfall model. As you know, the waterfall model is the earliest software development lifecycle approach that was used for software development, and it is also referred to as a linear sequential lifecycle model. It is very simple to understand, very easy to use, and in this waterfall model, each phase must be completed before the next phase can begin, so it means that there is no overlapping in the phases, right? Here we have a number of new defects introduced in each development phase. I will show you the distributions in the next slides, but like here, it is assumed that no new defects are introduced in the phases of system tests and acceptance tests. So we have a review and test software quality assurance activities serve as filters assumption. That means these filters, they remove a percentage of the incoming defects, and how can I say, they letting the rest pass on to the next development phase. For example, let's say we have if the number of incoming defects is 30, right, and the filtering efficiency is 60%. It means that 18 defects will be removed, while 12 defects will remain and be passed on to be detected by the next quality assurance activity. In the next slides, I will show you how typical filtering effectiveness rates change for other quality assurance activities as well. But for the moment, we know that filtering efficiency, it's same for every defect, and which is irrespective of its origination phase. We have incoming defects. It's at each phase, the incoming defects are the sum of defects that not removed by the former quality assurance activity, plus with the new defects created in the current development phase. We have the average cost. It's the average cost of defect removal at the phase it's originated is the same for all phases, and this is also can be called for like one cost unit. We have the cost of defect removal. The cost of defect removal is calculated for each quality assurance activity by multiplying the number of defects removed by the relative cost of removing a defect. That's how it's calculated. And we have the remaining defects, right? The remaining defects are not detected by the set of software quality assurance tools, and unfortunately, they are passed on to the customer, so they will be detected by the customer. So under these conditions, removal of defects detected by the customer requires the how can I say, they requires the heaviest of defect removal costs. We have a defects and filtering unit. I would like to explain more about this because in the software quality assurance model, each of the quality assurance activity is represented by a filter unit. I will show this filter unit samples like the tables in the next slides, but first I would like to talk about the parameters and the defects originated in different phases. Here we have defects originated in the requirement phase. We have the ones originated in the design phase and in the unit testing phase. Here you can see the abbreviations. We have defects originated in the integration testing phase. We have defects originated in the documentation phase. I would like to also mention about model parameters as well, so we can interpret the tables better. So we have model quantities. We have phase originated defects. We have incoming defects from current development phase and former software quality assurance activities. We have past defects to next quality assurance activity. We have removed defects in current quality assurance activity. We have a percentage of filtering effectiveness, and we have a relative defect removal cost, along with the total removal cost of current filtering activity and cost units. So here we have a filtering of design review activity. This is a filter unit. This is the table that I was talking about. So the filter unit shown in this slide actually represents the filtering process by the design review activity. Okay, this is our sample. So here we have a filtering effectiveness which is 50%, and 6 defects are passed from the previous development phase, which is the requirement review phase, and we have the 35 defects are due to the failures from the design phase process and introduced into this filter. So as a filtering effectiveness of this phase is 50%, like the total number of undetected defects passed to the next phase, which is the code review of unit testing, is 20.5. So while 20.5 defects are removed in this software quality assurance activity. So the resources invested in defect removal during the design phase amount to 27.4 cost units, where removal of defects passed from the requirement phase required 3.3 cost units for each defect. So how we can obtain this 27.4 cost units? It's we multiply, as I said before, we multiply 17.5 by 1 plus 3 multiply 3.3, and we obtain which is equal to 27.4 cost units. That's how the calculation goes. So we can say that, like the previous table, the previous filter unit, demonstrates the model that applies to a standard quality assurance plan that is composed of 6 quality assurance activities, which is also can be seen as 6 filters that are implemented internally by the developer. I would like to show you more of another. Before going into this figure, I would like to say that this standard plan does not include design inspection and code inspection. This is the plan I'm talking about. This filter unit. So an additional software quality assurance activity for removing the remaining software defects is performed for defects detected by the customer during regular operation of the software product. So it is assumed that the customer reveals all the remaining defects during regular operation of the software system. So now I can pass to another figure. The next table that I will be showing you, it's provide process-oriented illustration of the standard quality assurance plan model, and here we can see that, like, the activities is written here. The POD, it's the phase originated defects, as I mentioned before. So here we have a requirement specification activity, and we have the filtering effectiveness, we have all the other calculations, we have design activity, we have unit tests, and then we have integration tests, and we have documentation reviews, and we have system tests and operation by customer. So here, as you can see, it's the the filtering efficiency has a huge impact on the other filters, right? As you can see from the arrows here. So what I would like to say, like, as a summary, as my friend also talk about it, Arife, and my other friend will also talk about it in more detail, but I'd just like to give like a brief summary, like a chapter comparison of 2 verification and validating plans, right? So we have 2 plans. It's the standard plan and the comprehensive plan. So if we apply a given verification validation plan, we can compare alternative programs by supplying the expected percentage of errors to be removed in each screening stage for each activity, right? So the software quality assurance model deals with 2 aspects, which are the total effectiveness of defect removal plan and the total cost of defect removal plan. And we already mentioned that the software quality assurance model is based on 3 types of data, which is the distribution of the defects according to their originating phase, and we have a defect removal effectiveness according to the type of the activity and development phase, and we have the cost. The cost of the defect removal according to the originating development phase and the phase from which it was removed. So the software quality assurance model enables calculation of estimates for defect removal effectiveness and cost of proposals in regards to the structure of verification and validating plans. So that's all for the moment. Thanks for listening. Thanks for paying attention. And my friend Duygu will explain more about the subject in detail. Hope you like it. Thank you.
Hi, this is Duygu. Here I will show you how affect application of SQE model for comparing VV plans. And my other friend already talked about standard VV plan, which is process-oriented illustration of the standard quality assurance plan model. In this chapter, I will explain how comprehensive VV plan works, and I will also compare them. So we will receive exact outcomes regarding difference between them. I mean, these 2 VV plans. Here you see quality assurance activities and their effectiveness rates. My friend Arife already mentioned these numbers. Actually, I would like to remind you these data. Because I will use this data to provide a detailed explanation of comprehensive VV plan. You may see here 5 main defect origination phases. We use cost unit to calculate removal cost. The number you see are the cost units of each defect phases of each activity. The phases are requirement specification phase, design, unit testing phase, integration test phase, and documentation phase. Each of the quality assurance activities is represented by a filter unit. Let me introduce defects. IDIF means incoming defects. PDIF mean past defects. RDIF mean removed defects. RC mean relative defects removal cost. So, for example, if the number of incoming defects is 20, as you see in graph, and the filtering efficiency is 70%, then 14 defects will be removed, as you see in chart, while 6 defects will remain and be passed on to be deducted by the next quality assurance activity. The filter unit shown in figure presents the filtering process by the design inspection activity, where the filtering effectiveness is 55%. Six defects are passed from the former development phase. The total number of undetected defects passed to the next phase. all you may see the same flow all calculation. So every past defect of previous activity actually is the reference of incoming defect of next activity. At each phase, the incoming defects are the sum of defects not removed by the former quality assurance activity, together with the new defects introduced or created in the current development phase. So, we can say that if you invest in quality assurance in the earlier stage of the software development process, you will get higher the total of effectiveness of defect removal and the lower total defect removal cost. So here you also can see there is absence of important activities in standard VV plan. Those important activities like design inspection code and design inspection and code inspection. So these data mean to us SQA's additional SQE activities reduce percentage of remaining defects, cost of defect removal. Since additional SQE activities reduced cost involving defect removal and also reduce total cost of defect removal, we can say that SQE application, high quality SQE application save time and cost, and they are beneficial for better reliability, and they are improving the process of creating software, and they improve the quality of the software. You again see detailed comparison of the outcomes of the standard software quality plan and the comprehensive plan. I think it's quite instructive. There is a big difference between cost of removing. Thank you very much to take time to watch my video presentation. Have a nice day.